The same general principles that we learned in with acid-base titrations also apply to redox titrations, and you'll see there's many parallels here as well. In acid-base titrations, acids are titrated with a base, and bases are titrated with an acid. In redox titrations, an oxidizing agent is titrated with a reducing agent, and a reducing agent is titrated with an oxidizing agent. Hopefully that makes sense. In acid-base titrations, the titrant must be strong to drive the reaction to completion. In redox titrations, the titrant must be sufficiently strong oxidizing agent or reducing agent, depending on the situation, such that the reaction will occur spontaneously. Finally, in acid-base titrations, an indicator is added to signal when the equivalence point has been reached. In redox titrations, it's common that the titrant itself acts as its own indicator, since many species will actually change color when they get oxidized or reduced. Okay, let's take a look at a redox titration question. So we are told that we are titrating a 25 ml sample of iron 2 solution to the equivalence point. And it takes 16.7 milliliters of 0.0152 molar permanganate ion solution, acidic solution was needed. What is the iron 2 concentration? So first of all, we want to identify here that our permanganate ion is the oxidizing agent, and our iron 2 ion is the reducing agent. So we find those on the left and right hand side of the SRP tables respectively. Then I'm just going to copy out the half reactions for permanganate ion and iron 2 ion as found in the SRP table. Next, I want to balance the number of electrons being transferred. So I'm going to multiply my oxidation half reaction by a coefficient of 5. That way my electron transfer is equal to each other. 5 electrons lost, 5 electrons gained, and I can now join my two half reactions together. The whole purpose of writing this reaction is to be able to identify the mole ratio of when permanganate ion and iron 2 ion react with each other. So we can see it's a 1 to 5 mole ratio. So I'm going to take my 16.7 milliliters of permanganate ion and convert that to moles of iron 2 ions. So dividing by 1,000 to convert to liters, multiplying by 0.0152 moles per liter, and then using that mole ratio, 5 moles of iron 2 ion to react with 1 mole of permanganate ion. That gives me a total number of moles of iron ion of 1.27 times 10 to the negative 3 moles. Next, I want the concentration. So that number of moles was contained in what volume? It was in a 25 ml sample. So I'm just going to take that number of moles and divide it by the volume in liters, which is 0.0250 liters. That works out to a concentration of 0.0508 molar iron 2 ion solution. You might be wondering about indicators for this reaction, and as we mentioned before, in redox titrations, the titrant itself often acts as its own indicator. So for example, in this reaction, permanganate ion is a deep purple color. When it gets reduced and forms manganese 2 ion, that has a very faint pink color in acidic conditions. So you can imagine a situation where you are adding the permanganate from your burette, and that deep purple then is going to react with the iron 2 ion and become colorless. And so in this case, you'll know that when you've reached the equivalence point, when you add the first drop of permanganate ion, that doesn't change color. So the solution shows its first instance of that purple color remaining.